t squared or t to the negative 2. You take the first derivative of that, you get negative 2t to the negative 3, or negative 2 over t cubed. So on with the second derivative, you get 6t to the negative 4th. And plugging in the proposed solution to the 4y, the first derivative of that solution to the 5ty, and the second derivative to the t squared second derivative, you end up with 6t to the negative 2 minus 10t to the negative 2 plus 4t to the negative 2 equals 0, which does check out. And then when you confirm your initial condition, you have y of 2 equals, so your t is still t to the negative 2, which is 1/4.
Thanks. So for those of you at Jedi Math, what do you remember about initial conditions? What were they?
You could be given the initial condition of the derivatives as well, and then you kind of just go back from there.
Do you kind of remember it from an application perspective, why there was an initial condition?
To solve for.
I think without it, don't you there's like an infinite number.
That's correct. I actually taught with a German girl who used to take off points whenever the people forgot the C.
Right.
And then when the students came to argue about it, she'd say, well, you actually missed an infinite number of them, so I could have taken off more.
Right.
Never fight with the Germans. German math professors. Yeah, so what is it? It's actually, if you think about it, I'm going to show you a model tomorrow. Like all of these differential equations is about applications. And so it's kind of weird for me to put up stuff that has no meaning and then you start working on it, because for me it has a lot of meaning in applied mathematics. So one of the things that I was asked to do in the field of nutrition and obesity research is help write down a model that can help people stay adherent. That's the biggest issue with weight change, whether you're trying to gain or lose weight. You might think, well, who wants to gain weight? We've worked with anorexics. They need to gain weight. So you need to figure out how many calories they need to gain that particular weight and reach a goal weight. But then you also have the adherence issue. With anorexics, it's actually very difficult because they're fighting you on eating more. But on the other end, but this actually gives the clinician something to look at and say, are they on track or not? They might be saying something completely different than what they're doing. On the other end, people who have obesity and need to lose weight, you can give them a caloric deficit. Jenny Craig is a perfect example of that. They have two types of diets. I think one is 1,800 calories per day, and the other one is 1,600 calories a day. The Jenny Craig personnel actually told me, our customers are adherent. And I showed them, the models say they're not. And I showed them the Minnesota starvation experiment. It's a very interesting study that was done back in the 50s, I think, where they took participants and semi-starved them, 1,800 calories. So that was the higher Jenny Craig diets. They looked like concentration camp victims at the end of 24 weeks. So I asked the Jenny Craig people, how do you reconcile that piece? That's what happened when you had people in residence and you gave them 1,800 calories a day. They were nearly dead at the end of 24 weeks. So the models actually are based on the first law of thermodynamics. You can easily write one down. We're going to do that next class period. We're going to write one down. You might want to find someone that is trying to lose weight. Everybody has someone, a friend, a family member that's trying to lose weight, and ask them for their numbers. The numbers you'll need is age, initial weight, where they're starting from. That's the initial condition. That's where the initial condition, you'll know their initial weight. So most experiments, when you start them, you'll know what happens at the beginning. And you're looking at what happens over time after you perturb that system in some way. So that's a perfect example of an initial condition. When you step on that scale, that's what's your weight that first day. And then you'll need their initial weight and you'll need their height. And I think that's it. You need to know how physically active they are. But if you know the person, you'll know how physically active they are. We're going to bucket them into little, it's a very crude model we're going to put together, but we're going to bucket them into different activity levels. And we'll do that on the next class period so you can actually work with a real model. We've used these kind of models actually to keep people adherent. You can actually have these weight graphs that are generated from a differential equation. They plug in their age, their height, their initial weight, and their caloric deficit, and it shows what their predicted weight loss is supposed to be. And then their daily weights are collected with e-scales and then mapped onto that curve. And if they are away from the curve, they're not adherent. So it's been used by a psychologist friend of mine to keep them on track. And so this is actually a model that's been used, but not the one that I'm going to show you tomorrow, the next class period. It's going to be much more simple. But it does a good job. Okay, I did want to show you direction fields. Let me see if I have that in here. I do. I think I put it on your sheet. So maybe we'll look at your sheet. Yeah, I do have something here. Calculus is the most important class that people take. I know that sometimes I say even that maybe we should not teach calculus anymore. We should do data science or something different. Shame on me for saying that. Let's suppose I have something like y prime is equal to y. I don't know what I put. I can't remember what I put in here. Yeah, I put y prime is equal to y. So I know I have this. Pretend I didn't know how to solve it. A lot of things you write down, you don't know how to solve. Most things you write down that are interesting, you don't know how to solve. So if you have something like this, I do have some information. I have something about the derivative. And that class that you had in calculus tells you something about the derivative. If the derivative is positive, what's supposed to happen to the original function? Increasing. If the derivative is negative, it's decreasing. So, and you know something even about concavity from the second derivative. You can even relay it with the first derivative. So what I could do is I could say, okay, I could say, here are my t values. I'm going to start it at somewhere. And then y at t. These are like initial conditions. I call it t0, I think, in your little thing. So they're proposed initial conditions. I could take the y prime at t0 and say something about the curve. So I know something about the slope. So let's say t0 was 0 and y of t0 was 1. Then I know that the derivative at t0 is going to be 1, which is, it looks like y equals x, right? It has the same slope as y equals x. So then I could actually just say, okay, at t equals 0, y equals 1. Right? It's going to be like this, kind of like y equals x, for a little while.
And that's us picking the initial condition, right?
Yeah, you're just kind of picking the initial condition, say, at least for the beginning, I know this is going to happen, right?
Okay.
And I can even say more than that. I can say, okay, if the next leg of it, if it went up, this derivative is going to be even bigger. And we do know that higher slope means that's steeper. So I can tell you something more about that curve. So what I've done here is I've actually drawn out, this is my work. I just manually drew out what the slope, what we call a direction field or slope field looks like for this particular y prime equals y. So I gave you something different. Again, I gave you something harder. Sorry. I want you to try it. See if you can sketch that direction field out for number 2. It's one of my favorite ones.